it's element 39 again. This is the third video in my Chemistria series. This time, we'll be talking about the treasure of chemistry, the periodic table, and the curious patterns that it embodies. The periodic table brings joy to a chemist's eyes. If you look at it, it has everything you need: atomic weight, atomic number, or the number of protons in an element, and much, much more. The periodic table is organized into groups that are from top to bottom and rows that are from side to side. The elements are grouped according to their properties, and periodicity increases every time you go to the right. Instead of giving you a detailed statement of all the elements, I will give you the group properties first in this video. Let's start with the first column, the alkali metals. The alkali metals are highly reactive and dangerous. Francium, this little one here, will literally, if you hold it in your hand, will literally explode from the water in the sweat of it. In fact, this is the common trait of all alkali metals, that they react explosively to air and water, as a result of the outermost electron essentially being shielded from the proton's positive charge. They become more explosive as the atomic number increases, while the single electron in their last electron shells get more and more loosely bound. Among this group, hydrogen is an exception. Why, may you ask? Hydrogen, the lightest of the elements, despite its placement, is not an alkali metal. Firstly, this is because hydrogen does not like shedding into electrons, unlike its peers in the alkali group, because there is no other electron to repel it from a proton, making the electron-proton bond much stronger. Second of all, it's not even a metal, it's a gas, literally. Hydrogen is placed in the alkaline section because it has a similar electron configuration as one for each alkali, making for neat periodic arrangements. In reality, it should be placed closer to the non-metals. They are placed in the first group, or Ia. Alkaline metals, right over here, are similar to the alkali metals, except they have a lower electron shedding rate because this takes up more energy than shedding one electron, due to the fact that shedding two electrons takes up more energy than one electron. The majority of the alkaline group have practical uses, like the magnesium in Epsom salts that cure stomach ache, or the calcium in the dehydrated salt. Calcium chloride that acts like an effective water sponge in some particular experiments. Conversely, radium is a radioactive substance that is harmful in any quantity. Barium will kill you because it mimics the properties of magnesium and calcium, and beryllium will shred your lungs to pieces. Not a nice bunch. They are in group 2, or IIA. The transition metals, here to here, or on the D block, are generally safe to handle and are stable. They are known for their wide range of melting points from -38 degrees Celsius to over 3000 degrees Celsius, and the conductivity of many elements in this section. They have a very limited palette of colors, most being a silvery gray or bluish gray, and heaps of other colors, but out of many things there are exceptions. In the case of bismuth oxides, gold, and copper. A small group in the middle, called the noble metals, chemistry speak, do not oxidize or react with other things except when under extreme conditions. It includes gold, osmium, platinum, and tantalum. On a curious side note, if you look at the 7th row in the periodic table of the elements, and look at the transition metals explicitly, you will notice that all of them are the names of famous scientists, such as this one, Rutherfordium. It's named after the legendary scientist Ernest Rutherford, and Seaborgium is named after Glenn Seaborg. Located just before the transition metals, post-transition metals do what they suggest, more metallic than non-metals and less metallic than transition metals. They possess many of the qualities of metals, and here are a few. They are solid under standard conditions, malleable, ductile, good conductors of electricity and heat, and are very dense. The transition metals can include aluminium, calcium, lead, and tin. The elements of this block are very variable. Different versions of the periodic table list different elements. Some list elements that you and I would normally classify as part of the D block, such as gold, silver, or tin, while others will go for even more unconventional elements, one version even classifying astatine, which is part of the halogens. And even more shocking is that IUPAC, the International Union of Pure and Applied Chemistry, does not classify this as an official group. Because this is not an official group, there is no particular set of columns that people can assign owing to the number of variations. Metalloids, right over here, are a group of elements that form a diagonal line on the table. Metalloids have both non-metal properties, such as being very brittle, and metallic properties, such as having a sheen, and properties of their own, like being okay conductors of heat and electricity. When it comes to sharing electrons, they are totally ambivalent and are able to switch between charges. This is why one metalloid, looking at you, silicon, is used so frequently in the electronics industry because of its ability to be a conductor and an insulator at the same time. Silicon is used also because of its relative abundance and its purity. Non-metals, right here, are a group of elements that are not metals. But that doesn't mean that they are all gases. They just lack the properties of metal. They are bad conductors, brittle, and have high electronegativities and low melting points except for carbon. They are located in columns 14, 15, and 16 and include oxygen, nitrogen, sulfur, and phosphorus. Halogens, right over here, are especially electron-hungry gases that have an incomplete outer shell. Halogens, like non-metals, are bad conductors of electricity. They also have low melting points and boiling points, with fluorine having the lowest melting point at lower than -200 degrees Celsius. They are extremely reactive and all of them can kill. Halogens then bonded with alkalis from halide salts. Many people tried to isolate an element from this group, fluorine, and many were killed or injured in the process. The discoveries of fluorine were praised by the Nobel Committee for taming a wild beast among the elements. They occupy group 17, or VIIa. Noble gases are not what you think. No, they don't save the ladies of the periodic table from the villains. No, they don't have lots of jewels, and no, they are not born to the aristocracy of the table. All elements in group VIIa, or 18, all possess the same properties. They are noble in a standoffish way. This is because every noble gas, except for helium, have full p orbitals that have 6 electrons, which make them have full electron shells. Helium, only having an s orbital, has 2 electrons. Interestingly enough, 3 of the noble gases can bond if forced to with pure fluorine, mainly xenon, argon, and krypton. They are located in group 18, or VIIa. You may have heard about the rare earths. They are used in mobiles and TV sets and lots of electricity-related objects. You may think, the word rare means uncommon, so does that mean that the rare earths are uncommon? Well, no, it's actually quite the opposite. Some of the rare earths are nearly as common as other plentiful elements are. The real reason why electrons cost so much is due to the demand for the pure elements in real life and the difficulty to extract these elements that add to the cost. Almost every sample you will find of a certain rare earth will always be contaminated by one of its brothers. The lanthanides bury their electrons way down in the inner P, S, and D shells, with the F shell staying mostly empty. The lanthanides are used in electronics because the lanthanides, firstly, are part of the transition metals and are good conductors, and secondly, they oxidize at +3 and +2, making them attractive to electrons. Located just under the lanthanide series, you'd think that the actinides are similar in properties to the lanthanides. No, in fact they are completely different. Starting from actinium to lawrencium, almost all of them are man-made and have short half-lives. The exceptions are uranium, thorium, actinium, and protactinium, which are natural and have longer half-lives, with uranium having the longest of 4.47 billion years. Hi, it's Element 39 again. I hope you have enjoyed this episode of Chemistria. Thanks for watching. Please like or subscribe for future videos.